Questions you might want to ask before I go over anything? Sections 4.1 through 4.4. Okay, you could expect for a format.
4.1 there was no math, right?
Yeah, 4.1, 4.2 are mainly conceptual. 4.3 started Newton's laws, or Newton's second and third law, which was F equals ma, so there was some math in 4.3. Okay, and a lot of math obviously in 4.4. So we're going to have about 7 or 8 multiple choice questions. Between 6 and 8 short answer. And then 4 free response. That's the format, just to give you a heads up. Okay? The free response, you're going to have to do the first 2. Then you can choose one of the next 2, and then choose one of the next 2. Same as last test, same format. Okay? I'm only putting the choice up there just so you can see different versions of problems, but it's really the same thing. When I put 2 questions to choose from, it's really the same topic we're being tested on, except I might give you acceleration and say find mu. But in the next one, I might give you mu and say find acceleration. Okay? For the free response, you can be guaranteed to have an inclined plane. Okay? You'll have 2 of them at the end. You'll choose one of them. Okay, so one of these, you'll choose one of 2, and it'll be an inclined plane. You will definitely have a question about weight and different planets. You will definitely have one with a force at an angle. So an example, like you apply a force, you pull on the table at an angle of 45 degrees. You have to find, say, the friction force acting backward or something else. And then you will definitely have a problem with friction on a flat surface. So I'll say horizontal. Okay, the inclined plane does have friction as well. The inclined plane is definitely the toughest problem for a lot of people. We did a good job of it yesterday in class in here, and I was very happy. And then we went over it in the lab, the idea. We didn't go over the theory again. I hope that by doing the problem sets, you saw so many inclined planes that you're pretty familiar with them by now. The sample problems I put up from 4.4 with the solutions under documents and handouts had a lot of inclined plane problems. So if you're still struggling, even after we go over stuff today, that's a good resource to look at tonight if I don't put up the problem set solution, if they don't all get turned in. 4.4 sample problems under documents and handouts is a very good thing to study. Okay? So that's the general idea for the test. For the multiple choice, you could expect things mainly from 4.1 and 4.2. Some stuff from 4.3 and 4.4 though. Remember how we talked about like the coefficient of static friction and how it's greater than kinetic friction? So I could give you a multiple choice and say the coefficient of static friction between 2 surfaces is 0.8. What could be a possible coefficient of kinetic friction for the same surfaces? And you have 4 choices. Which one should you look for? The one that's what? Greater than, equal to, or less than 0.8? Yeah, less than, because kinetic friction is less than static. So if I give you static and say which could be kinetic, look for a number smaller than that. What else do we know about our coefficients? Can they be positive or can they be negative? Can they be negative? No, they cannot be negative. They can be greater than 1 though, which we haven't seen an example of that yet. But just to make sure you understand. So if you get an answer bigger than 1 for mu, it is possible. But if you get something like 10, it's not reasonable. Anything bigger than 1 is usually something that's like 1.1, 1.2. Mu values much larger than 1 don't really exist. Okay, just to give you a sense of numbers in number sense. So when you're taking the test, you could say, that answer doesn't seem reasonable, right? So if you ever get a negative mu, you got to go back and see you might have made a mistake along the way. Being able to calculate the force of friction. So if I ask you for the force of friction, you get a number, and then I say, what's the mu value after that? What was our formula for force of friction? What's the formula? You have this on your sheet, but go ahead. Yeah. So, remember, if part of the problem says, determine what FF is, you can look and find what FF is and get a number for it in the x direction. But then if it says find mu, all you got to do is take that answer and divide it by Fn. But you might need to go to the y direction to find Fn. Okay? Angles. Forces at angles. What do we remember for forces at angles? If I pull on a box Okay? Say I'm like on the ground, or it's like a big crate, and I have to pull on it, and I'm pulling down on an angle, just to make this a little tougher. Let's say I pull at that angle. Where would theta be in this diagram? Where's the theta that we are familiar with? Bobby?
Between the box and the arrow.
Like here?
Yeah.
It's not there, and that's the one people would use right away. If you use that theta, you have to switch your signs to cosines. Do you remember where? Yeah, so we got to keep like going like this. Remember, we have to make believe there's a horizontal. Always add in a horizontal. That's theta. Remember, theta is between the vector and the horizontal. The vector is given. That's the ray coming off here. That's the force. Where's the horizontal? There's the horizontal. Okay?
So to get the theta, you do the
If
angle,
you were given
minus
this,
that angle. Alright.
if you were given this, though, if you were told that this angle were, say, 70 degrees, then you can't use that. You would use 20 degrees. Okay? So again, this is always your angle. Now, with that said, remember FPX and FPY are really projections. Let me draw that.
Wasn't me this time. That happened to me actually. I was closing my past apps.
That's what they all say.
I started playing on my past apps.
All right, so just because it was funny because it's EA Sports,
I'm sorry. I was closing it and it opened it.
Always check your
All right, Elliot. Wait. No, I was closing it.
Yeah.
now what game was it at least?
FIFA, man.
FIFA?
Yeah, there's 2 teams.
That's a good game. All right, so in this diagram, take a look. These are what the projections look like, and this is what's really interesting to look at. When you apply a force at an angle, part of it could be positive in the x, but then take a look in the y, it's negative. Because I'm pulling down on this box. So imagine I had a rope tied to the top of the door, okay, and I pulled on that rope, this chain right here. This is what I'm doing. That's exactly what's happening right here. I'm pulling to the right, so the x component, FPX, is positive. But I'm also pulling down. So FPY turns out to be negative in this example. So when you draw your equations of motion and you write up your equations, in the y direction it's going to be a minus FPY. And in the x direction it's going to be a plus FPX. And remember, FPX and FPY are also defined. We talked about what those are. Who remembers what FPX and FPY were defined as? How do we find the x component? And remember, we're not on an inclined plane. Inclined plane we did yesterday, and that was finding FGX and FGY. But for a pull, how do I find the components? I keep writing P instead of FP. I don't know why. What is FPX? Nobody remembers this? You take the original force and multiply it by what? Cosine. Good. Okay, that's what FPX would be. And FPY, see again, it's the weirdest thing. I don't know why I'm doing that. Okay? And remember, when you write your equations of motion out, okay, when you write your equations of motion, for something like this, let's say that we had friction acting backward. Okay, against the motion, there's FF. We've got the weight acting down, FG. Got the normal force acting up, Fn. All right, and let's say the problem was at equilibrium. It doesn't really matter at this point. I just want to show the equation. In the x direction, you would have positive Fpx minus Ffk. Okay, we'll say it's moving at a constant velocity, and that equals 0. And in the y direction, you would have positive Fn minus Fg, but then minus FPY. And that's what I wanted to indicate. That even though FP is one pull, part of it could be positive, part of it could be negative. Part of it could be positive, part of it could be negative. So this negative FPY, because it's being pulled down, appears in my y direction. And then at that point, you would plug in what you know. FPX, you know, it's FP cos theta. FFK is mu k Fn, and that equals 0. So this is your governing equation in the x direction here. And in the y direction, you don't know much. You know Fn is still there. Fg is really mass times gravity. Fpy is Fp sine theta. And that equals 0. And this is your governing equation in the y direction. Okay, so again, a lot going on for a problem that's pretty simple with just one force being applied to it. See how much you have to really do? If you don't write these out, that's fine. You don't need to write these out. You don't have to write them out on the test as long as you write them out in the equation correctly. If you could remember where they go in the equation, you don't have to sit there and write those out every time. So your diagram would look like that. You have to draw a diagram to start. You can't come up with these equations elsewise. Then go to your x direction, come up with your governing equation. Go to your y direction, come up with your governing equation. Then, based on what the problem is asking, you would have to figure it out. Okay, so let's say you were looking for mu k up here. Let me point to it with the cursor. Let's say you were looking for mu k up here. If you're looking for mu k, you need everything else in that equation. So Fp is probably given, theta is probably given, but Fn isn't given, remember? So what do we do to get Fn? Yeah, go to our linking variable in the y direction. Find Fn here. By moving mg over and moving Fp sine theta over, you can get Fn. Plug that expression in up here, and you could solve for mu k.
Why wouldn't you just move Fn over by itself?
You could, but it would move it over as a negative quantity.
Yeah.
And you'd have to divide by -1, which would give you the same answer as what I just did. Here's my theory. If you're isolating a variable and it's already positive, leave it alone. So see how Fn here is what we're going to isolate? We're trying to isolate this Fn. It's already positive, so leave it. Because if we move this, Mike, it becomes negative, then we have to divide by negative. Exactly. So just move over these two in one step. You guys should be, second nature by now and moving things around. Literally, rewrite this entire expression that I'm circling right here on the right-hand side, but with positive signs. That's what moving it over really means. All right, so this is a good sample kind of question for the mathematical part. Again, a force applied at an angle. This would be like a 10 or 12 point question. Maybe 6 points for finding one part and 6 points for finding the other. Okay?
Why are they set to equal to 0?
Because I said that it was moving at a constant velocity. So ma would be 0. If there was acceleration, then you set them equal to ma and find the accelerations. Or plug in, depending if it was given. Yeah?
How is the force equals ma accurate? Like on one of the problem sets, it said you're moving at a constant velocity. What's your net force? I don't remember. But if you're moving, there is force, right?
If you're moving, there is some force, but the net force, if you're moving at a constant velocity, is 0.
Okay.
Okay, so like here's the idea, ready? If I were to drag this notebook or this set of keys across the table at a constant velocity, that means that the force I'm applying is equal and opposite the frictional force, and they're balanced. So the friction force might be -1 Newton. I'm pulling with +1 Newton. What's the overall force? 0, because it's moving at a constant velocity. The minute I start to accelerate this, then it's moving with a net force in your case, because I diagrammed it, negative x direction. Okay? So I was moving left. That's why I said negative x direction. Other questions? What other stuff has been perturbing you or confusing you? Or
Inclined plane.
all right, you want to do an example?
Yes.
Inclined plane? Okay. One thing that you're going to notice is that a lot of inclined plane problems are the same solution generically. And if you did enough of them on the problem set, you probably picked up on it after a while. You kept getting for ones without acceleration, you kept getting cosine 90 minus theta over sine 90 minus theta when you solve for mu k. But for ones that there were acceleration, it was a little bit different, obviously. So let's do one where we're finding the acceleration. We haven't done that yet. Okay, we're finding the acceleration of the box. And then I can even go further and say, now find the distance traveled. And we can use
Yeah,
that.
there was one you said, I think.
Okay. And we could use what we know from kinematics to do that part. If you know the acceleration, and you know, say, the initial velocity and the length of the ramp, you could find the final velocity. Or if you knew the initial velocity and the time period, you could find the distance traveled or the final velocity. So we could expand those questions and hit upon the previous stuff. I saw a hand shoot up real quick before I get started.
Yeah, you said that you had an hour-long video for the 4-4. But do you have all the other ones too, or just 4-4?
The video that I put up under my videos, not those class videos, is an hour long of all of 4-4.
But do you have them of the other lessons too, or just for
What other lessons?
4-1, 4-2? Just
Yeah, they're all up.
Oh, okay.
Oh yeah, they're all there. Go to, it says like the section below the class videos, you should say Mr. Howell's videos.
Okay.
4, 1, 2, 3 have been there for a while.
Okay.
4, 4 I just put up recently though. It's just a long video, that's what I was mentioning. Okay? Yeah, so don't watch the whole thing, just look at the part that you need help on, obviously. It might help you. Alright, so let's pick an example here, okay? And I'm gonna need your help. I want some numbers. What's a mass we could use? Give me a mass. 4? 4 what?
4 kilograms.
Yeah, kg.
Kilograms?
Oh, wait, you can change it to.
I mean, you could give me a number in grams and we could have to convert it if we wanted to do that.
Are we gonna have to do that on the time?
I'm not going to, you should always be ready to do that. Absolutely. And any test. That's a given, yeah. If you're given in grams, you should convert to kilograms.
So
Assume
that
you
was-
should know that.
That was grams.
Okay.
Would be 0.04.
Yeah.
It's 3 decimal places.
3 decimal places. Very good. Very good. Let's say we have an incline of 15. I heard it first. Sorry, Nick. Nick, you give me the length of the ramp, Nick.
20 meters.
20 meters. I'm going to put D for now. Instead of X or Y for displacement, I'm going to put distance. And I'll label it on the diagram. Okay? So we're clear as to what we're talking about. Let's see.
Does that say theta?
Yeah.
Theta equals 15. What else do we need? We need mu. We definitely have to have mu. Here's the deal. If we're finding A, we need mu. If we're finding mu, we need A, right? Vice versa. So what's a mu value for this example? Since it's moving, it's kinetic. 0.427. Okay, that works. That's fine. Okay, and we're going to find the acceleration down the ramp. We're going to find the acceleration. Focus. What are you laughing at?
Wait, Mr. Howell,
Yeah,
are they allowed to do, you did problem sets with someone from
Yeah, I
another
did
class?
problems.
That's fine.
That's fine?
yeah, because you're grading now. In the past, it was you and Fernando, remember? But he's doing math. So as long as you're okay with that, is that all right with you?
Yeah, that's fine. I didn't know that, okay.
Yeah. Last year I didn't because again I had 2 separate things and stuff, but I don't mind, especially with Dropbox, since you can, put stuff together.
Alright, sounds good.
All right, so how do we start this? What?
No one from the other class handed it in there,
No one?
just one person.
Oh, jeez.
They were, no, I think they all have free like next period.
They do, and it's not due until the period after. All right. So, what are our givens? What do we write on the diagram here? What do we got? What are our givens, and what can we draw on our diagram here? So let's draw our box, and what can we write for our forces? What's the first force?
Gravity.
Or any of the forces. Gravity's the obvious one. Okay.
Gravity isn't in the X or Y direction, right? It's just.
It's straight down, but we're going to break it into its directions in a minute. So get ready to erase that, or put another color soon. Philip?
And is normal force
Good.
4 kilograms?
And where's normal force acting?
Oh.
Yeah, but in
Like
which
diagonal
direction?
to the right.
Good.
The normal force is 4.
Remember, the normal force is always acting out of the plane at a right angle. So if you want to draw your right angle in to remember that, it might be useful.
Why is it 4?
It's not 4, FN.
Oh,
Where do you see 4?
I thought I heard 4 say 4.
Oh, no. Out of the floor. Okay. What else? Force of friction. Why is friction acting up the ramp? Yeah, because it's moving down the ramp. All right. I saw your hand go up, Maria, so you can answer this next question. What do I do with FG now? What do I do with FG? And I'll do it in white. Good. So we draw the Y version of FG like this. Okay, along the Y-axis. Remember, this is your Y-axis now. Notice this inclined plane is different from yesterday's, right? Remember yesterday we drew it falling this way? Okay, I purposely did that so you can see it doesn't matter. So now we have to tilt our head like this. Here's our Y-axis. Okay, and here's our X-axis. So this is positive X now, down the ramp. This is negative X, positive Y, negative Y.
If we were going up the ramp, would you look the other way?
If the object were sliding up the ramp, no, it's just that the object's motion would be in the negative x direction now. That's all that would change there. Okay? So this is FGY, and what's FGX? How do I draw that? What is it doing? What is FGX doing?
Pointing the box downwards.
Yeah, very good. It's pointing downwards or down the ramp. Okay? So what we've done is we've technically created a triangle here. And I'm going to put a triangle in dashed red ink so you can see it. Here's the triangle we've created. Okay, which is tough to see at first, but it's right there.
Oh.
Okay, I'll highlight it with the marker or the cursor real quick. Red ink was a bad choice. So here's the triangle that we've technically created. Okay? And this is where we came up with our theory from last time, where we're going to use sine of 90 minus theta and cosine of 90 minus theta here instead, because again, the angle theta we're going to be using is this angle we want right here. That's what theta is going to be.
Why doesn't the triangle have to do with FGX?
It does, but FGX, make believe you take FGX and slide it down here. So imagine if you drew FGX right here, Mike, instead. It's the same thing. Okay?
Oh, it's the same length.
Say again?
Is it like the same length?
Yeah, it'd be the same length and everything as the one we just had up there. Okay? Alright, so we have all our forces acting on this object. We can go ahead and take a look at our directionals. In the x direction, what's pulling down the ramp again? FGX is down the ramp. And down the ramp is positive in the x direction for this problem. Again, remember, just look at your y-axis. Here's your y-axis when you tilt your head. So if this is the y-axis and that's positive for y, this is positive for x. It doesn't matter. You could call up positive for x as long as you're consistent in your equations. Is that clear? As long as you're consistent in your equations. Since it's moving down the ramp, our acceleration at the end should be positive or negative? Positive, because down the ramp is positive again. Remember we drew FGX here as a positive? So the answer we get for acceleration better be positive. Had we drawn up the ramp as positive, the answer we've gotten for acceleration would have been negative. That's all that would change. Okay, but it's the same thing. It still means down the ramp. What's keeping it on the ramp or keeping it up?
Wait, when you do minus FFA.
Good. And what does that equal? MA. We're looking for A. Remember, people? There's no zero in this problem. We're trying to find the acceleration down the ramp. We're never finding the acceleration in the y direction. Have you noticed that by now? Okay, because what's the acceleration in the y direction going to be? It's going to be 0. Gravity is not going to be. The acceleration in the y direction as I move this way, there's no vertical motion. So there's no acceleration. It's only left to right here. Okay? No vertical motion.
Technically, since it's sliding like downward and to the side.
But we tilted our axis. We tilted our axis. And it's going along the x-axis that we just made, isn't it?
Yes.
So it's all in the x direction.
Oh.
That's why we tilt our axis. I'm glad you asked that, Mike. Mike's making a good point there, right? He said it's technically going down at an angle. So it's going down the y and the x. But in our minds, or in our problem, we created the ramp surface to be the x-axis. So this object is moving only along the x-axis. It's not moving along the y-axis.
Should it always move along the x-axis?
You always want it to move along one axis, which is why we tilt our axis here.
Can you do it along two axes? Or?
Technically, yes, and the problem would be a lot messier. You'd have a lot of thetas and different angles, and you have a ton of trig involved. This simplifies it greatly, greatly. One other thing I want to point out, I said you're not usually finding acceleration in the y. You are sometimes. Remember the elevator example? Remember the elevator example? Okay, that involved acceleration in the y direction. So I don't want to make that statement that you're never finding it. Sometimes you are, but with inclined planes and horizontal motion, you're not finding a y. Elliot?
On the problem set, there was one where like the ramp went down to the left, so the acceleration was negative.
Yeah, that's not a problem.
No, it's not, but on like the test, will you say if it's going to the right or the left? Or should
You could just draw the ramp however you would like to, whatever you think you're more comfortable with. Either way, you'll get the same answer. So if you get an answer in this problem, the acceleration will be like, say, positive 5. But if you did it the other way, like you were saying a moment ago, it would be negative 5. But either way, at the end of the problem, you could say, it's 5 meters per second squared down the ramp. Okay? And I'll know from your diagram whether it should be negative or positive, so it's fine either way. If it specifically says something, I don't know why, or if I gave you a diagram, then keep it the way it is. Okay? You may, I don't know. Like,
Wouldn't the elevator question be more of like the short, like the writing ones? 'Cause-
yeah, so the elevator question is a good chance that'll show up as like, free response, or not free response, short answer, multiple choice. But I did do one with mathematical in the elevator. It's in your notes. Okay? We did an example all about mathematical with the elevator, so.
So if you were to draw the ramp the other way, do the signs of like the X values change? Do you know what I mean? Like if you were to draw the ramp like the opposite way, so like
Yeah, FF would be positive, FGX would be negative, and the acceleration you get in the end would be negative. Yep, absolutely. All right, let's take a look at the y direction. In the y direction, what do we have? What's acting in the positive y direction? Positive y direction. Fn. And Joyce, what's acting in the negative y direction?
FGY.
And what does this equal?
0.
With confidence, right?
Yes.
0. Again, the object is not moving off the ramp. It's not moving in the y direction. It's not falling through the ramp and breaking through the ramp. So there's no acceleration along my y-axis. There's no motion there. So it's got to be 0.
Doesn't it technically equal MA, but since A is 0,
Yes.
you do like the arrow thingy?
Yep. So if you want to do that, you can do that. That's fine. Absolutely. Okay? So Mike is just saying we should really write AY. We should really write AX. But this just goes to 0. Absolutely. Okay? All right. At this point in time, what are we trying to find? So what are we going to divide everything by? M. Mass. See the mass next to acceleration? We want to get rid of it. We want to get rid of it. Let's see. Yeah. So we're going to get, what is FGX? I'm going to rewrite everything, I guess. I should do it all in one step. What is FGX equal to? mg for the mass times gravity. Cosine. Good.
You just plug in.
So I'm taking the first equation for the x direction and rewriting it. So remember, force of gravity is always mg. Always mg, that's the first part here. But we're looking at the force of gravity in the x direction on an inclined plane. X indicates cosine, inclined plane indicates 90 minus theta. Minus, what's FFK? What do we write for FFK? Mu k Fn equals max. But I want a by itself, so just put ax here and divide it all by m. Okay?
Wait, friction is equal to the end.
Fn, always. Again, formula sheet. If there's something you need to study tonight and it sounds stupid but it's simple, study the formulas. Make sure you understand what they are and what they mean. You have got to always know your formula sheet like the back of your hand. Okay, so please study that tonight. So that's our expression. We've got everything except for normal force. Again, that annoying normal force, right? Hate that normal force. But it's pretty easy in this problem because look at your y direction. In your y direction, all you got to do is move FGY over and you get the normal force by itself. So let's do that in orange over here. So add FGY over here, you get that the normal force is simply FGY. Because again, this is 0. It's a big 0 right there. So that's what the normal force is. It's FGY, but what's FGY? Reese, what's FGY?
mg sine 90 minus theta.
Good. Okay?
No, I asked a question.
Does it make sense?
Yeah.
Sure. So that's what Fn is. We got this from the y direction. This is our what variable again? Linking variable. This is our linking variable, analogous to time. We take that expression and plug it in for Fn. It's going to be a messy problem now. Can you all see that? It's going to happen? I'll write in.
And the reason why we didn't divide by m yet on the x is because...
There's no m in the mu k Fn. Take a look.
But then once we plug in...
Then there'll be an m there. Yes. Good, Mike. You're noticing already. So Mike, take a look at this, everybody. Mike noticed the following. we're probably going to divide by this m and cancel like we've done. There's m here, but there's no m over here. But once we replace this expression in for fn, there'll be an m there. And there'll be an m in all three terms, so we could factor out the m on the top and cancel, or just cancel all the m's, like we did yesterday. So did we need that mass of 4 kilograms that Joyce gave us in the beginning?
Yeah.
Turns out we didn't need it. And there's probably a possibility that you might not be given a mass on one of the problems. You might be like, how do I do this? There's no mass. But you need to do generic solution because of that. Okay? So I'd practice going through this process. So let's plug this in right here, please. Giving us okay, so again, all we did was plug in. Let's go ahead and cancel our m's. Remember, if there's an m in every term, you're good to go. And the first term, this is one term right here. This is one term. It's all multiplied. There's a subtraction symbol, which means this is another term. Remember, this subtraction is not another term. This is inside of the sine and cosine. So term number 1, God bless you. Term number 2, term number 3. That's what I mean by all the terms. M is in all of them. So we can drop off all those m's because of that. It's the same thing as what we did yesterday where we factored out m from here and here on the top and then canceled the factored out m with this m over here.
Could you just use this same equation for like all of these types of problems? So like you just memorize that equation. Do you have to do all that work before? Can you just put that down?
If you know the generic solution to these equations and you write up the generic solution and then manipulate it, that's fine. But that involves some work to do that, you know? Okay, so here what he's saying is this. Remember though, things can change suddenly. What if there's now a force that's also pushing up the ramp? Instead of, to continue with Elliot's question, because it's a really good question, take a look at the x direction in this problem. Everybody see it? FGX minus FFK up top. What if I was pushing up the ramp also? And it was a problem where not only was friction helping me, but I was pushing up the ramp so it didn't come down as fast. There'd be a negative FP in addition to that negative FFK. And then the solution would change slightly. So do you see what I'm saying there? So if you can remember the particular situation that we're in right now, and you could find that it's the same on the test, if it is, if it's not, you need to change it though. Do you follow what I'm saying? So again, if there was somebody pushing up the ramp, you would have a minus FP right there, showing that you're pushing against gravity, against
By
FGX.
pushing up, you mean pushing the opposite way
Of the motion.
thing is going down.
Correct.
Alright.
Hence the negative FP.
Alright.
Okay? I saw another hand pop up somewhere. No? Again, though, we're not doing that in this situation, so I erase that for now. But again, that is a possibility. So let's just solve now. We're pretty much done with this problem. Okay? Solution is G cos 90 minus theta minus mu k. I could factor out the G actually like this. See how there's a G in both terms up top? Everybody see that or no? If you look at the top, there's G here, right there, and there's a G right there. So you can take that out in front. When you take a G out of here, you're left with cosine 90 minus theta. Take G out of here, you're left with negative mu k sine 90 minus theta equals AX. So to expand your minds a little bit, let's see who can think. If I was on an unknown planet, okay, and I had all the tools in the world to measure stuff, but I didn't know what the gravitational constant on that planet was, what could I do? How could I find, like on Earth it's 9.81, right? So we know to plug in 9.81 right here. But what if I was on a planet where there wasn't any sort of G value that was known, but I had all of the material and the lab material and the technology, okay, to measure stuff? How could I figure out what the gravitational constant on that planet is?
Measure the friction and then work backwards in the problem.
Exactly. If you could measure mu k like we did yesterday, remember we measured mu k with that device? If you knew mu k by measuring it, you could measure the angle with a protractor on an inclined plane. You can measure the time it takes to get from the top of the plane to the bottom. If you know the distance, you know the initial velocity, you could find the acceleration. So you could figure out everything else experimentally, really, and then solve for g on that planet. So that's a way of finding the gravitational constant on a planet, which is pretty cool. There's an easier way to do it. There's an easier way to do it with free fall. Okay, with free fall, using y equals 1/2 at squared, solving for acceleration. So you could do that also and drop it. But this is just the inclined plane solution to finding g. This is like an AP Physics topic. Okay, in labs in AP Physics, you do things like determine and create your own lab on how to find the gravitational constant on a planet if you're only given an inclined plane and some measurements. This is how you would actually do it. Okay, and you have to invent your own ideas. So it's an extension of what we're doing, but the idea is the same. Okay. What were you going to point out, Ken? What were you going to point out?
Oh, can't you just find the mass of the person?
You could measure the mass using a triple beam balance. Is that what you mean?
Yeah.
You could measure the mass, but you would then need a scale, I guess.
You just said you have all the tools.
Trying to think, yeah, I guess that would work, but then the scale needs to be calibrated on that planet. So you might need G before you can even have the scale. Let me think for a minute. The problem with measuring the mass... Say again?
If mass is the same everywhere, you have the force of gravity.
You have the mass. The mass is the same everywhere. But I'm wondering if the scale... I guess a spring scale would work on other planets. Yeah. A spring scale would work. It should work on other planets. You could do that also. Okay, but again, this is the inclined plane approach to finding G. Other questions about the test? Other questions? We still have some time. No? Newton's laws? What does Newton's first law tell us?
An object at rest will remain at rest, and an object in motion will remain in motion unless I have
Yeah, good. Inertia tells us if I'm in motion, I'm going to stay in motion unless something slows me down. On Earth, gravity slows us down vertically, friction slows us down horizontally. Okay? So that's why if I drop this object here, right, if I drop this, it's in motion. It wants to stay in motion. But what outside force stopped it from staying in motion? The normal force from the table. Okay? Clearly the table is what stops it from moving. Now, Newton's third law says for every...
There's a reaction.
Okay, for every action there's an equal and opposite reaction. Equal and opposite reaction. Now, remember, that has to do with one specific body. One specific body every time. So we did the example with the nail. We hit the nail, and the free body diagram is on the nail. Okay? So we're looking at a specific object. A specific object. So, I'm trying to think of the example that I can go through that would help. If I wanted to lift something out of a well in the ground, this is a good example. Okay? Explain how Newton's third law would be used and what's going on, how Newton's third law is applicable. If I'm lifting something out of a well, okay? What would I attach to it and how would it work? What would happen? How would be Newton's third law?
Pulley?
Okay, you gotta have a pulley, good. So some sort of a rope, and then what do you do?
Pull the rope.
And what happens? What does the rope do?
Pulls it on.
The rope, like, the object pulls down with the force, and the rope has to pull more, with more force in order for the object to come out of the place.
Imagine it's just a rope and not on a pulley, because the pulley part is making your answer. So you literally just have a rope.
Yeah.
You pull on the rope. What does the rope do to you? The rope pulls back on you for sure, right? How are you going to be able to actually lift it out? What does your force have to be?
It's greater than the force of the bucket and the rope.
Yeah, your force up. Your force up has to be more than the force of gravity on the bucket for it to have some acceleration. But when you pull on that rope with a force of, say, 75 newtons, even though it's moving upward, the rope still has tension in it of 75 newtons. It pulls back at 75 newtons. If you pull with too much force on a rope, what's going to happen to it? It'll break. You'll exceed the yield strength of that rope. Newton's second law says
F equals
Okay, F equals ma. So as you increase the force on an object, the object's acceleration will also increase. Force and acceleration are directly related.
So that matters.
Numbers on the free body diagram.
You don't. If a free body diagram gave you numbers, that's fine. Or if you had numbers on it, that's fine, but you don't need them on there. As long as you list your givens on the side, if you put the numbers on the diagram, then you're kind of listing the givens there also. So if you were to put like a diagram and you wrote FP on the diagram, instead of just writing FP, you wrote like FP equal 100 Newton on the diagram, I'll take that as your given also. Okay? So you can do that, that's fine.
If you said you were gonna give us like mu values, and we would have to like, is that gonna be like a short answer, or is that gonna be like
Multiple choice or short answer. Stuff like that with mu and comparing the mu values and relative mu values.
What do you mean by that?
So what time does this period end at?
10:13.
1 minute.